Welcome. Let's see if we leave the door open here, if we have others joining. Plenty of, what about 20 people or so who are joining us online. Welcome there. I'll try to track if anybody's screaming online about not being able to hear. I'll get on another device as soon as I can. But yeah, welcome everybody to the 32nd, I believe, Kuehnast lecture in climatology and meteorology, presented by those of us at the Department of Soil, Water, and Climate. So I am Peter Neff. I am a faculty member, assistant professor just across the street in soil, water, and climate. I specialize in polar science and ice core records of past climate. The Kuehnast Endowment was set up by the family of Earl Kuehnast in 1992, and we're honored to have their support at the Department of Soil, Water, and Climate for the teaching and research in support of climatology and meteorology, our students, and this lecture series in the department. So it's very great to see a good-sized group of Kuehnasts here. So you guys want to wave or raise your hands if folks here know. We all appreciate you being here. Yeah, 3 generations of Kuehnasts are here, I'm told. So thank you guys so much for taking the time, and I look forward to socializing after the lecture. So we will have some brief remarks from our department chair, Brent Williams, here for the next 10 minutes or so before we introduce our speaker, Dr. Elizabeth Barnes, who's joining us here from Boston University. And after the lecture, somewhere a little past 4 o'clock, we'll then move out to the atrium here, have some light refreshments and chit chat before we all splinter off, and then the family joins us, some of the faculty and students in the department for dinner with Dr. Barnes. So I'll hand it over to you, Brent, and then I'll fully introduce Libby once you're done.
Excellent. Thank you, Peter.
Let's see. Fans. Yeah.
Okay, welcome everybody. Thanks for joining us here today, and thanks to you online who are joining. Starting off with a quote from the amazing Dr. Jane Goodall, who we lost yesterday. Only if we understand can we care. Only if we care, we will help. Only if we help, we shall be saved. So I love this quote for starting us off today and thinking about what we do here at the university. It really is striving to understand as a starting point. That's what our research is. That's what our classroom education is. That is helping the public understand through our extension work that we do. It's really our mission. What are we trying to save? So I'm thinking I'll start a new tradition with the Kuehnast lecture and start the introduction with this figure, and we'll do a state of the globe from year to year. I hope I'm here long enough, and the series goes long enough that we can view this in different lights and look back at our accomplishments, but thinking about sort of the getting a temperature on the globe, getting a temperature of the state of our research, the state of our nation, not to get into politics and policies. Here is not really the intention of this lectureship, but I've learned from our extension educators that just working with data is the place to start. That's the place to start the conversation. And so here we are from 1960 to today. Our CO2 concentrations in our atmosphere currently, we're at 425 parts per million today. The consequences of having more greenhouse gases is we have a resulting rise in temperature over that time. And relative to the average across the 1900s, we're at 1.2 degrees Celsius warmer than we were last century. It's a pretty rapid change that's occurring. So we'll look at this next year. We'll see how we're doing. That's sort of our, if we're taking a temperature on our planet, it looks like the thermometer is reading a little bit warm. There's something we take to break fevers. I forget what that is. Okay, I won't get into that, but I said I'm not going to get into politics. The state of our Department of Soil, Water, and Climate Starting sort of at the university level, I want to report that we have a new president at the university, President Cunningham, and we have a new provost. And we've seen a renewed interest in St. Paul campus. The president has been over several times, which is sort of unprecedented in past leadership. The Board of Regents has been here frequently. And we are making it onto the new strategic plan for the university, a reinvestment in the St. Paul campus. So the details to follow on that, but that is exciting here in our College of CFANs. So now coming down to the department level, I'd like to just sort of provide some updates from this last year, on some recognition, some accomplishments from the department. First thing I want to show is these are our new, since we all were in this room together last year, those of you that were here, these are our new graduate students that have joined us. There's 16 new students. Raise your hand if you're a first year student. Thanks for joining us. It's really exciting. Our enrollment numbers continue to go up. Even with all of our challenges, there's people that want to come and study in the department and study in our Land and Atmospheric Sciences graduate program. Our undergraduate enrollment, we support the environmental science and policy, environmental science policy and management undergraduate major. Enrollment is up in ESPM. Our soils classes enrollment is up. Our water science classes enrollment's up. So things are feeling really positive there in our classrooms. These are the list of last year's award winners for our graduate student, mostly travel support that comes from our various donors. We're in the process of reviewing applicants for this year's award winners, but I just mostly want to point out, we do have the Earl Kuehnast Family Endowment Award, the Zanner family, the Chang family, her family, Baker family, and another one in the room is the Satish and Cynthia Gupta award. So we will announce shortly in a newsletter the current year's award winners. Okay. There are more awards. I always feel like I'm going to leave somebody out if I start sharing awards that were recognition from the past year, but I did highlight some here. Our DEI committee within our department. It's a time we're hearing a lot about DEI and programs and universities. We were recognized in our department for our excellence. We won the Inclusive Excellence Award. The committee did. Carrie Jarko, who's I saw in the room. She's not going to like that I let her. She's hiding somewhere. Oh, Carrie Jarko, our graduate program coordinator, won the 2025 Borealis Exemplary Staff Award for the entire college. Anna Cates, one of our faculty members, won the Outstanding Extension Faculty Award. A number of our graduate students were recognized with various fellowships and awards for research and public engagement, a number of things. Congratulations to all of them. I wanted to highlight Professor Fabian Fernandez and Randy Kolka, who this last year were named fellows of the Soil Science Society of America in 2025. Tim Griffiths, who I saw earlier, is in the back of the room here, was recognized by American Meteorological Society as a 2025 fellow. So congratulations to all of you for those are sort of career-long recognition for the full body of work. So quite an honor. And I get to recognize one of the Kuehnast family members here. Kathleen Kuehnast was last year won U of M's College of Liberal Arts Alumni of Notable Achievement Award, which was quite an honor. Sharing a picture here with Peter Nutt in the middle and Kathleen on the right, and Dr. Heidi Roop on the left. Out in DC, they were all in DC this last year. Here they were together at the U.S. Institute of Peace. If you want to learn more about the status of that, you can catch Kathleen afterwards. Currently being impacted. So the reason that Heidi and Peter were out there is that Professor Heidi Roop this last year completed a year of service in the White House. She was Assistant Director for Climate Services in the Office of Science and Technology Policy, as well as the Deputy Director for Services with the U.S. Global Change Research Program. And that was also quite an honor to be recognized for her leadership in that position. Quick update from our department. How we operate from day to day is these amazing people, our administrative staff. Since last year, new to our group is Ariana Radi, who is our administrative coordinator. Nora Poole is our communications specialist. Amber Kevelin is our finance professional. Sue and Carrie have been with us for a lot longer. Today we determined our new department administrator. The offer is going out tonight, so stay tuned. I am not a great department administrator. You don't want me doing your payroll. I hope everyone let me know if there's continued problems with it, but we're so excited. Also, promotions from this last year, we had 6 faculty receive promotions. Anna Cates was promoted to associate extension professor. Lindsay Pease and Heidi Roop received tenure and promotion to associate professor. And Satoshi Ishii, Dan Kaiser, and Yushin Yao were all promoted to full professor. We did have retirements. These started around last year, but they're all official now. Tracy Twine retired this past year. Jay Bell and Peter Snyder were all faculty in our department. We're working currently with faculty to try to recruit a couple new hires in our department. So that's what we're working on currently. Tom Graff was with the soil testing and research analytical lab and with the department, which the lab used to be in the department. Tom retired after 50 years working there. Quite amazing. I don't know if anybody is 50 years at the same place. One of my last notes here is this last spring, we had a really big change in the department. Since 1961, the USDA ARS Soil and Water Management Unit was with our department, sat with us, ran research labs, co-advised graduate students, wrote research projects together. They served as adjunct faculty in our department, these folks here. Since a year ago, they have all, they're no longer with USDA ARS through retirements and deferred resignations. Their labs were larger, technicians, researchers, and other staff. We went from about 20 folks down to, we have three people in the unit now. It was a great loss for us. There was over 50 graduate students that had graduated from collaborations with our ARS folks. Here's a picture of us celebrating together. This is the last day we were all together, and about half the folks in this picture are no longer with us in the department. I was going to also share just this past summer, we lost 2 really great soil, water, and climate community members. On the left is Melvin Giles. Melvin was our inaugural departmental community research fellow, and Melvin was really important in the communities of St. Paul, Rondo neighborhood, and Frogtown communities. Led a whole bunch of community projects and was just like one of the most amazing humans I've had an honor to meet. Unfortunately, fell ill. And Al Lohese was a PhD student who graduated with us in 21 from the Land and Atmospheric Science program. Al went back to Africa and worked with local community farmers on farming practices and did some really amazing work, and unfortunately also fell ill this last summer, and we lost both of them. So one one sort of thing just around the corner and within the next few weeks here, University of Minnesota Climate Adaptation Partnership, MCAP, is going to be hosting the Midwest Climate Resilience Conference. If you want to learn more about this or attend in future years, or you have interest in it, contact Maria within MCAP. And then the last note is, if you're not on our newsletter, please join our newsletter. We went from last year being really understaffed and having 0 newsletters to Nora Poole coming in, is who you'll contact if you want to join the newsletter, to offering a once a month newsletter, and now we're doing 2 a month. So we're doing it every other week. There's so much awesome stuff going on in the department. So if you're not on there, please join. I would love to share more regularly what's going on in the department. So thank you so much. I'll hand it back to Peter.
And thank you, Brent, for all you do for the department. So it's my privilege now to introduce our speaker and our topic for the day. Again, similar to Brent, we want to avoid politics, but I think it's safe to say that it's been a tough year for the motivation of public service as a core value. And I didn't have the pleasure of knowing Earl Kuehnast, who was a longtime state climatologist for the state of Minnesota, but I would hope that you would agree with me that a value that he shared with everybody was that of public service. And so, in these challenging times where it's not exactly clear in the United States how our federal funding system is going to move forward with respect to the science that we do in service to the society and to the public, it can feel a little unclear what to do. I can certainly say this week I had quite a few moments of not exactly knowing what's going on these days and why we should keep forging ahead and serving the public and really having that as our core motivation. So I don't have a lot of deep wisdom to say about that. Besides that, there are plenty of challenges ahead still in the areas of soil, water, and climate, certainly with respect to climate science and climate change. We can't shrink away from those challenges just because they are global in their scale and that they are deeply inconvenient. So in thinking of how to move forward, what better than talk about the hot topic of the day, artificial intelligence. So we'll be hearing from Professor Elizabeth Barnes for the next 45-50 minutes or so about explainable artificial intelligence for Earth system prediction from black box to window into the future. That hopefully will just take us forward into all of the amazing assistance that we might get in addressing considerable challenges in climate science and Earth system science with that tool of AI. So let's see, I need to remember to get my notes out to introduce them because there's a long rap sheet we need to go into. So as we thought if we were to invite this year, I should remember to thank Julieta Vincosa in the back here, a postdoc in Dylan Millay's atmospheric chemistry research group. She was my co-chair this year of the Kuehnast committee, and she was the one who immediately thought of Libby as an excellent speaker, and thankfully Libby accepted. So in addition to being the incoming Dalton Family Chair in Environmental Data Science and Sustainability, and also Professor of Computing and Data Sciences and of Earth and Environment at Boston University. Libby's also an alumni of the University of Minnesota. Her parents are here with us. Her father is a professor in the civil engineering department. And so Libby was a double major in math and physics with honors at the University of Minnesota before going on to do her PhD in the atmospheric science department at University of Washington, where we briefly overlapped without encountering each other as graduate students. Let's see, Libby has been, her achievements have been honored with a number of awards. So she is a fellow of both the American Geophysical Union and the American Meteorological Society. She was recently awarded the Presidential Early Career Award for Scientists and Engineers by President Biden in January of this year. Congratulations for that. In addition to being a fellow of the American Geophysical Union, she's also a McElwain Medal winner from 2021. So just a few things on the list here. So without further ado, I hope you'll help me welcome Dr. Barnes here to the University of Minnesota, and we look forward to learning more about AI. Yes, if I can get this to stop doing things around.
Okay.
Okay.
How's the volume? Can people hear me in the back? Okay,
A little low.
okay, I get louder.
Oh.
Yeah. So I typically people say turn it up and then they go, turn it down. I go, oh, please don't give me a thumbs down yet. I haven't said it. All right.
Okay, trying to get it all set. Is that okay if this?
Typically we can get rid of that.
Over here? That's it.
Yeah, you can.
What am I missing?
All right, hold on.
Oh, there you go.
Here you go. I put it in controls. And I don't know how to do it. There it is.
Yeah.
We did it.
Perfect.
Okay. Thank you all for coming. As I get excited, am I in charge of my own volume with this thing?
Yes, and
Okay, that's dangerous.
I don't,
All right,
it's actually not immediately clear to me how to change the volume on that.
great.
Maybe move it further away,
Yes.
or if we need to just dispatch it all together.
All right, we're gonna go down there. We'll see how that works. Okay, well, thank you so much for coming. Before I get started, it was already mentioned, I went to school here. So I thought briefly, since I'm gonna talk about the science I do today, I would touch on the importance of undergraduate research while I was here. I got to work on a variety of things. So I did math and physics, that was already mentioned. And I started off wanting to be a particle physicist and actually did most of my degree here in high energy particle physics as a focus, which sent me to Chicago, sent me to northern Minnesota to work in this underground mine where they were shooting particles from Chicago through the earth to end up at this mine as part of this Minos experiment. It was so cool. I loved it. These particles called neutrinos. But one day, one of these these detectors caught fire, and everything was going to be fine. It turned out fine. But the postdoc that I was sharing an office with got really freaked out. And she's like, I've spent my whole life on this one project. And that was the day, I still remember that day, going, I want to work. I don't want to spend 10 years on one problem. I want to work on 10 problems in one day. I want to work on lots of things all the time. And so the next day, I started emailing faculty here at the University of Minnesota in a variety of topics saying, would you ever hire a physics major as a graduate student? And thankfully, they all encouraged me, yes, don't worry, you haven't completely ruined your chances of getting a PhD. So I will mention that while I started really thinking about earth science, it was one of those most complex topics I could think of. It would allow me to study the atmosphere, study the oceans, study the land, study ice, study, deep within the rocks within the earth. I could sort of do anything I wanted. And if I ever got bored doing that, I could also bring humans into the mix and I'd have a career, right? I'd never get bored. And so that was the type of work that motivated me to go into climate science. But also there was this piece of me that loved data. And actually it was 2 projects I did here right at the end. The bottom right was the first paper I ever wrote. I didn't actually know that's what the biomass looked like until yesterday when I pulled up this picture. So that's a biomass in rivers, and we were trying to scale it to understand if we take a few measurements in one location, could we scale it up to understand how much was in, say, an entire river basin. And then the other project I did was looking at the packing of granular media. So these were little ball bearings that we put on a shake table and we shook them to see how they would pack. And this was the first coding experience I really had. And I loved it so much. And so this is really going to bring me to the type of work I do now, which is I really sit with one foot in each camp. I love writing code. I love thinking about data science. I love fitting lines through data, right? And then I love the understanding and the earth science side of figuring out why things work the way they do and the causal structure connecting everything to each other. And so that's going to take me to my talk today. Oh yeah, I did graduate, and there I am with my parents, just to prove. So there I am graduating in May of 2007. So today we are going to first start part 1 with an overview of AI applications in weather and climate. Then I'm going to talk about what we call XAI. We love our acronyms. So explainable AI for climate prediction across time scales. And then I'm going to end thinking bigger, thinking about how we use these tools more broadly to anticipate human Earth system futures. So that's the goal here. Also, I will note you're going to see some really pretty pictures throughout this talk. I cannot draw. at all. These were not drawn by me, but this was in collaboration with a professional artist at Heartwood Visuals. And this is something I actually am really passionate about, is how, as physical scientists, can we continue to do a better job at the communication part, not just in our speaking, but also art is a wonderful medium to use to communicate what it is that we do. All right, so artificial intelligence or machine learning, we can use it for so many things in the science that we do. You could use it for, say, tailored predictions of understanding severe hazard forecasts. So on the right is a NOAA product telling the probability of a particular weather event. And on the left is a machine learning algorithm trying to do something similar and actually being quite successful. This particular tool now is being used operationally at the National Weather Service. But we can also do it for things like what we call post-processing, or taking blurry images of the coastline we get from climate models and making it much more high resolution. There you see that on the right. These days, we can use AI to improve our physics-based models. So our physics-based models actually struggle quite a bit with clouds. They have for decades, and they still do. And one of the big motivations originally when AI started coming into the mix in climate science was, can they help us with this incredibly complex problem of how we simulate clouds? Another thing that I already talked to some folks here today about is I'm really excited about machine learning specifically to merge lots of different kinds of data together. You can also think of different data sets, and the scientists that use them speak different languages, and it's often a translation barrier of how we work together. And one of the things I think that's exciting about machine learning is it may act as sort of that tape or that glue that helps us start to make progress by working together. So I actually see it as a great tool for interdisciplinary work, and I'll talk a bit about that. It's also important for visualization. So right now on the bottom, this was one of the first companies I know of. This was an NGO out of Canada that started putting together images. You can put in your address on Google Maps, and it will pull up what your house looks like flooded or on fire or under poor air quality. Yeah, people are looking at me like, why would I do that? But the idea is to communicate more sort of viscerally. This is what a changing climate could look like. On the top, this just came out in the MIT News a few months ago. It's taking satellite imagery and helping folks see what it might look like under after a flood. So helping visualize what that could look like. And then finally, a big area right now that's just been exploded the last year or two is deep learning weather and climate models. So these are full models that I'll talk through that replace the physics with machine learning. And don't worry, we'll talk about the pros and the cons to that throughout the talk. But what has been incredibly, I guess, maybe daunting is there isn't just one of these models that has come out, or two, or three, or four, or five, or six, or seven, but this is just the list here from about the first 9 months of 2024, okay? These models are coming out. There are so many, and it's because unlike our previous process-based models, these AI models are much easier to build and train. And so everybody's doing it, including some of these big companies. So one person might ask then, okay, there's all these applications, but why would I use AI at all? I put it into three categories. So one is to do something faster or cheaper, right? So we need to run all these simulations. Maybe we need to make weather forecasts, and we'd like to do more faster. Another is to do something better. I brought up clouds as an example. We struggle with simulating clouds in these models. Maybe AI can actually help us do a better job than we have in the past. But finally, and I think for this audience, being at a university, we are also there to do science and learn. And the big thing here is AI can also help us learn something new. So it's possible, and this is one of the things I love about using it for science, is sometimes it may only be as good as the tool we already had, but it allows us to probe the question in different ways. And that's what I want to hopefully excite, especially the graduate students here, as what this tool can be used for. Is it sort of a paintbrush, and you can make new kinds of ways of doing science with it. Okay, so in my group, my sort of spiel is we develop and implement AI tools to leverage our imperfect models in support of Earth system prediction across time and space. And these models are inaccurate. I want to be very clear. None of the models I'm going to grab data from today are perfect. They are inaccurate, but still invaluable parallel universes we can use to try to collect data and merge with the observations that we have. And then we can ask questions about when, where, and how are environmental conditions predictable. And also I like to always point out that I get to be the spokesperson, but this is work done by my wonderful group. This is us in Colorado. We have since moved to Boston just about 2.5 weeks ago. So we don't have a picture yet, but they're doing so much of this wonderful work. So you will also see little faces in bright pink, by the way. Sorry, just a note. There's not enough bright pink in professional talks. So anybody giving one soon, this is fuchsia, okay? So you will see bright pink circles around faces in the bottom right-hand corner throughout the talk, and that those are the group members that have been working on that topic. Okay, so I'm going to break my story here down into 3 pieces. We are going to start at the long time scale, large spatial scale. So we're going to start by talking about climate change, and then we're going to move to talking about forecasting on shorter time scales. So first of all, when we talk about climate change, we were already introduced to some of those temperature plots at the very beginning. And as you can see here, we know, or we can talk about the world and what it might look like at different warming levels. So like 1.5 degrees above C, degrees C above pre-industrial, 2, 3, 4. But one of the big things is the question marks at the bottom. And that is, when are we going to hit those numbers? That is actually a big question right now. That has to do with the sensitivity of our climate to greenhouse gases. So there are many folks trying to fill in numbers for when we might expect as a world to hit those different temperature or warming thresholds. But this is a hard problem. I already mentioned that, well, first of all, we can't take observations of the future so far, right? So one of the things we need to do is combine our understanding with our physics-based or with our models to try and predict what the future might look like under these different warming. And the problem is each of these different colors is a different climate model, okay? And each of these 3 panels shows different future scenarios of how humans may change their emissions in the coming years. On the left is not doing much, right? Same sort of status quo or even more extreme. And on the right is extreme mitigation. Well, I'm not going to say extreme, is some mitigation, right? And unfortunately, when we talk about those different warming levels, we see that the models disagree on when we cross those lines. And they disagree by a lot. We're not talking 1 to 2 years. They can disagree by decades, which has major implications. So one question is, how do we take all this information? I already mentioned they're inaccurate, but invaluable. How do we take all this information and try and get the best prediction we can for the real world? So there are lots of ways to do this. This is the way we chose to do it, which is we took the data from these climate models and we put it into a neural network. So imagine the year you were born. All are valid, okay? Imagine the year you were born, and you can imagine for that year having a map of the average temperature on the globe for that year, right? And everybody's will be a little different. And what we're going to do is feed it into a neural network, and we're going to ask the neural network how many years until that world hits 1.5 degrees above pre-industrial or 2 degrees above pre-industrial. And the reason we can do this is we're using climate model data where we know the right answer, okay? So we actually do a little bit more than that. We don't just say predict how many years until we reach the threshold. We have it predict probability distribution. So we have a certain quantification of some of the uncertainty associated with that prediction. And when we do that, we hope for a plot that looks something like this, where the true answer or the label or the target for you ML people is on the x-axis here, and the prediction by our network is on the y, and you want it to follow along that one-to-one line if it's doing a good job, and it looks like it's doing okay. All right, this is what you want to see. But this is actually boring. I need to prove to you that it does all right. Fine. But now what we're going to do is say, but this isn't a climate model. This is the real world. And I say, yes. Now we have now trained a network to take in maps of temperature and say how many years until we hit 2 degrees. And now I'm going to put in maps of the real world. And I'm going to say how many years until this hits 2 degrees. So these are maps of the actual temperatures, of average temperatures for these different years. So 1980, 92, 2016, and 2021. And we're going to put those into the network and ask, given what it's learned about these relationships, how many years until we hit these different temperature thresholds. And we can do this for every year since, for example, 1980. And we'd expect if our network is doing the right things for the right reasons, it should go down about 1 year per year. So every year we get closer, we should be 1 year closer, okay? And I would say this looks pretty good. We're about a -1 year per year slope, but some of you are sitting in the back and you're going, what about all the years before that? It's sort of flat. Or what about that bloop? Do you see the little bump? Well, turns out I actually like that it was wrong at this point. And the reason is that was when Mount Pinatubo erupted. And for those of you familiar, when a volcano erupts, it launches a bunch of stuff into the stratosphere that tends to reflect the sunlight and actually cool the surface of the earth. And this neural network didn't learn about volcanoes. And so it saw a slightly cooler earth and said, you're further away from hitting, in this case, the 2-degree threshold. And now you might say, well, that's a problem. I actually like it. It shows that it hasn't been overfitting, and I can actually understand when it's getting it wrong and why it's getting it wrong. Actually gives me a bit more trust in how it's doing its prediction. So ultimately, after all of this, we can actually come up with some predictions of how many years this world, the real one, has until we hit 2 degrees C under these different scenarios. And while other folks have are outputting predictions like this, I think our big result is that we have a higher likelihood of reaching 2 degrees, even under that low scenario than previous estimates, given how this model is taking different patterns and bringing them together for a final prediction. Now, we are going to come back to this, so don't worry. But before we do that, this was for the whole globe, but nobody lives on the whole globe at once, right? We live, in this case, we're in Central North America. And one of the things we did with the follow-up paper, it came out just last year, was that could we do the same process, but now focus more on a regional scale? Furthermore, this approach just assumes the climate models are good enough and has been training just on climate model data. And you might think, well, what if the climate models are wrong? Well, then my predictions will be wrong. And that doesn't feel right either. So what we're going to do is, instead of training on climate model data and just predicting the observations, we're going to do something called transfer learning, which is incredibly powerful. And I highly encourage anybody interested in doing machine learning for their science applications to consider this approach. Is we train on climate model data, and then we fine tune, we tweak it with the limited observations that we have. And it makes it then better suited to make predictions for the real world. We then use that fine-tuned model to predict our observations. And in fact, what we can show is the black line here is the observations. All those gray thin spaghetti lines, those are the climate model predictions. And you can see how they don't fit the black lines very well. Our base network, when trained, is that teal blue line. You can see how it's not aligned with the observations, right? Those are those biases, those are those errors in our climate models that we know about, but we can't get rid of. But when we do this fine-tuning process, we align better with the observations, and once again, have more confidence in our final predictions. Furthermore, we reduce the uncertainty significantly based on this approach. And please don't look at all this. The point is, we did it for lots of different regions and can show that ultimately this machine learning with fine-tuning significantly is constraining our projections and suggesting thresholds will occur sooner than anticipated. Okay, but this is about science, not just about making predictions. So anybody sitting here going, okay, you have your black box, but how in the world is it making these predictions in the first place, right? What is it doing? So what if we could learn which regions of the globe are most important or most relevant for the predictions the network is making? And that's where that learning something new comes in, right? So sometimes this is called opening the black box. Machine learning often gets the idea of a black box. There are now many papers. I'll tell you that this concept of explainability or explainable AI is a huge area of maybe not huge. It's a large area of computer science. There's a lot of folks working on it, but also we need physical scientists as well First, making it intelligible to those that don't have CS degrees. That was actually a really important contribution, right? And again, showing how to use it for science. So there are now many papers in the geoscience specifically focused on folks like yourselves who maybe aren't computer scientists or AI computer scientists, but want to know how to use XAI approaches. And just as an example, there are many approaches out there. I love talking about this. If you want to talk after, I can tell you about more. But here's one example of one way we use these explainability techniques. So imagine you've trained a neural network, to tell you if a cat is in an image. Okay, you've done it. It does pretty well. And you put in a new picture of a cat. Here it is. It's very cute. Goes in and it outputs the probability of 0.8 that there's a cat in the image. And you say, okay, but where did 0.8 come from? Why 0.8, right? Well, what these methods do, these are called attribution methods, is they take that 0.8 and they propagate it back through the network and ultimately make you sort of a colored heat map of where the network was looking when it decided that there was a cat in the image. And if you look, you will see it looked where there is a cat to determine there was a cat. Some people are not impressed. Okay. This is part of the challenge of these XAI approaches. Have we learned anything new here? Maybe not. But in my application, if you see where I'm going, it's predicting how many years until we hit 2 degrees. I'd love a heat map that looks like this, that showed me where on the globe it's looking when it makes its prediction, right? So we'll get there in a second, but first I want to sell you on these techniques. They are not the end all be all, but they are incredibly powerful. And ultimately, as a scientist, our goal is to understand why. So if you ask, why should I care about XAI? You might say, that's easy. We care about why. Turns out I have met people that do not care about why. All right, so how do we respond to them? Well, a few things. One, to gauge trust. One of the most important things for a human to gauge trustworthiness is to understand the thing that they are trying to gauge trust in. So by understanding what the network is doing, we might be able to decide, would I trust this to, drive my car, for example. Another reason is to fine tune and optimize. We've used this multiple times in our science when our network is not learning what we want it to learn. And now we have to go in and try and fix it. How do you fix something if you don't know where it's breaking? And so we use these approaches to go in and figure out what it's doing wrong. And finally, again, to learn something new, which is the example I've been talking about. So our ultimate goal is to understand causality. This is not causality. This is still correlation, but is a step in the right direction. So we're going to go back to this problem. We're trying to predict how long until Central North America is going to hit 2 degrees above pre-industrial levels. And the network has made a prediction. And we ask, why did it update its prediction? What in this transfer learning process, when I brought in observations, did it change? Put another way, what were the climate models doing wrong that the observations made it do better at? And we can create these heat maps. And these are the regions of the globe where those observations were important updates for what we were learning from the climate models alone. So there are a few locations here associated with, like desert topography, but the big area here is the Southern Ocean, where we know that our climate models are struggling. So I've gotten to start talking with oceanography colleagues about what these could mean, also regions of ice. Okay, so these really help us understand how that fine tuning with observation shows us relevant climate model biases. So that's that learn something new piece. Okay, so we're going to start to zoom in a little bit. We're going to talk about temperature trends. So the world is warming. We know that. We've seen multiple plots already today. And if we take a single climate model and we run it 100 different times with slightly different bits of noise, we'll get 100 different worlds, all simulated by the same climate model. And if you put in greenhouse gases, they all warm, right? That's one of the reasons as scientists we are confident in climate change and its drivers. And this is an example of 100 of those worlds showing the trends in temperature from 2021 to 2050. And you should see they're all a little different, but they're all red, right? It shows the climate is warming in all of these. But if you take these same simulations and you only look at the next, say, 10 years or 2021 to 2030, these are the trends that you get. They're not all red. Some of them even are blue, meaning they're cooling. These are all worlds with the same amount of CO2. The reason is what we call natural variability or internal variability. So like the noise of the climate system can get in the way, right? So some years are just going to be hotter than others. Some years might be colder than others. And in fact, so natural variability on these smaller timescales is much larger than the climate change signal. That's one of the struggles with the communication, right? It can still snow and have a climate change. So what this means is knowing what the future holds the next 5, 10, 15 years is not just about climate change. It's also about understanding the noise within our climate system. Put another way, this is for a location in Chicago. This is a climate model. There are 100 time series on here. And they also show climate warming. And if you take the average of all of those, that's what we call the forced response. That's climate change, okay? And also, for those interested, do you see all I say wiggles in every talk I've ever given. So do you see all the little wiggles on there? You might think, oh, you need more data to average those out. Those are actual signals. Those are lots and lots of tiny volcanoes that are going off that ultimately have an actual measurable impact on global temperature. Not just Pinatubo, not just the big ones. All right, so when we take that average, that's our forced response. But we could take one of those gray lines, and that's number 40, for example, and this could be a world we actually live in, right? We don't live in a mean, we don't live in the average, we live in a single realization. So we could be living in this teal world, or we could be living in this purple world, right? Which is number 32. And when we look at that, there's both the climate change signal, which is, again, these global warming projections. Then we can use AI to leverage these models to understand the future, which I showed you already. But we can also zoom in and start asking questions like, do you see this abrupt cooling that happens in this particular member? Could we have predicted that ahead of time? Is this something we could see coming? This is that climate noise, right? That's just inherent in our climate system. And so in our group, we're using AI to explore the predictability of the climate system days to years in advance. So that makes it sound really easy. And sometimes I get some eyebrows like, oh, of course, just predict the weather and climate. What's the big deal, right? So I want to be clear, climate prediction is incredibly challenging. It's really, really hard. People have been trying to do it for a very long time. And this is something, okay, I'm going to nerd out for a second. This is something that I have found surprises my computer science colleagues the most and often gets them the most excited to work with me. When I point out that unlike almost any problem they work on in climate science and geoscience, our goal is never to make perfect predictions all the time because we know it cannot happen, right? Chaos will win eventually. So instead of the goal being to make perfect predictions all the time, we want to make the best predictions we can when they are available, when the system allows it. And that is very different than, is there a cat in this image? Or what's the next word in this sentence? So put another way, a bit more scientifically, we have to look for specific states of the Earth system, what we call forecasts of opportunity, that lead to enhanced predictable behavior. And then we need to take advantage of those when they're there. Okay? And AI is perfect for this. And put another way, what we're trying to do is take a bunch of noisy data where 80% of it's just a blob that we may have no hope, but maybe 20% has a signal, and we're trying to extract that signal out of all of this chaotic noise. And in fact, impossible predictions may be hampering our AI learning because so many of these machine learning approaches were designed to assume your goal was 100% accuracy. And that's just not my goal. Instead, when we look for these more predictable states, for example, you might say, give me what's an example in the climate system? There's something called the Madden-Julian oscillation for those atmospheric scientists here, which is a set of storms that propagates from the west to the east, starting in the Indian Ocean, and propagates around the globe on approximately a 30-day time scale. And I say approximately because it's actually more like 30 to 90 days, and sometimes it dies in the middle, right? If it were truly periodic, this would be easy to predict. But the nice thing about this Madden-Julian oscillation is when it's present, it sends waves through the atmosphere that ultimately dictate where the storms go in the mid-latitudes, and either to send rain, for example, to Seattle or to Southern California. And so if we know what the tropics are doing, we can make predictions in the coming weeks of who's going to be wet and who's going to be dry. Many people may be more familiar with what's called the El Nino Southern Oscillation, or El Nino and La Nina. That operates on approximately 2-3 year timescales. And it's another phenomenon that helps us have more confidence when it's present, where it will rain, where it will be hot, where it will be cold, etc. These are the sorts of features we're looking for in the climate system. So as an example, this is some work that was done by Frances Davenport and Emily Gordon, formerly in my group, to predict ocean temperatures in the coming 5 years. What we did is we designed a neural network, or what they did, to take past sea surface temperatures as input and predict if the future at any given point would be warmer on average or cooler than normal. Okay. So they did this, they trained their network, they worked really hard. We're using climate model data, which we have a lot of. It's not even the real world yet. Okay. And they go and they do it. And this is their accuracy. So remember, we're predicting one of 3 classes, we call them. And the way we've designed it is 33% is random chance, right? You just randomly guess one of the 3. And if you look at my color bar, what color does that look like? Approximately random chance, right? So you might see this and say, you can't make these predictions. We can't predict what this ocean's going to do in a 5 year time scale. But this is when you look at everything, when you look at all predictions. If you use the neural network to tell you when it's most confident, I haven't told you how we do that, but that is one of the things you can use a neural network for. It can estimate how confident it is. If you use that, and you say, well, we're only going to look when you're confident in your prediction. Suddenly, we start to see patterns emerge where we do have skill. And if you say, when are you really confident? We have even more skill. So this is that whole concept of forecasts of opportunity. If you look at all forecasts, many of them are not good. But if you only look when you have confidence, when there's a signal there, then it turns out you can do much better. And I'm hopeful that this approach actually will lead to going beyond the weather timescale when we talk about our forecasting. Even more, they did this, they took their neural network that was trained on climate model output, and then they said, well, we have real world data, let's see how well it does. Can our neural network forecast the real world? And in fact, on the far left, it looks like the answer is no. But if we only look at forecasts when the network says, I have an opportunity here, I think this one's right, we actually do start to have skill. And in fact, these are regions of skill that we know from oceanography, that the way the circulation works actually leads to skills during certain times. Okay, so going further, these explainability approaches can help us identify the sources of predictability. So not just say, I think I'm right, and I think I have a good forecast of opportunity, but we can ask, where is it looking to get this confidence? Where is it looking to make these predictions? So going back to the same type of problem, predicting, in this case, land temperatures over the next 5 years, we can train a neural network to take in sea surface temperature maps and predict land temperatures in the coming years. And then we can use these explainable AI approaches, remember the cat, where we go backwards to create a heat map, to say, where did you look to make your prediction? We can end up with heat maps. So this is, instead of a cat face, this is regions of the ocean that the network used to make its forecasts. Okay, and what we see in this case is, depending on where it's predicting, you may be able to see there's a little red dot. We're predicting different locations. So when we're predicting for Mexico, it's using what we call the Kuroshio extension off of Japan as a source of information, which we know is actually a source of predictability within the climate system. When it's predicting for Canada, it's using both the Atlantic and the North Pacific. When it's predicting for the Midwest, here, I had to put something on there, in the Midwest, it's using the El Nino region to make its predictions. So this is one of the ways we can use to gauge trust and potentially learn new sources of predictability. But something else that's nice about this is that even making predictions for the same location, so this is off the west coast of the US, because the network is nonlinear, because it can come up with more complex relationships, it can identify different periods with predictability coming from different parts of the globe. And that's pretty cool. All right, so we've done this for these longer time scales, predicting, again, days to years in advance. I have quite a few folks working on this time scale. And we can go to even shorter time scales, like what we call the subseasonal to seasonal prediction range. So, in 2 or 3 weeks, how much will it rain? So that we're working on that time scale as well. However, I'm not going to go into that because I want to come back to this idea of a digital twin or these AI weather emulators. These have just exploded over the last few years. On the left is one of these AI models, and on the right is our sort of best guess of what the real world looks like. And I bet you if I hadn't labeled them, you would not have been able to tell which was which. This is, I do not say this lightly, this is revolutionary in the last few years for our entire field of earth science. Now, this was made by NVIDIA. This is one of the many large tech companies that's getting into the game of AI for weather and climate prediction. I will point out NVIDIA, I have colleagues there, they are wonderful, but they like to make pretty movies that do not show you whether it's any good at all or not, okay? So I'd like to talk about that. But NVIDIA is not the only group doing that. This is a sort of a time series of many of those models coming out that are big players in the game. And the black line there is sort of, give or take, we can go into nuances later, the state-of-the-art dynamical models. So that black line is what you want to beat if you want to beat the physics models. And you can see in the last few years, many models have now gone above that black line. You'll also notice they're plateauing. And I argue that's because they're starting to realize that predicting the weather is hard. Okay, which is why we should keep studying it. But anyway, okay. Also, they're expanding beyond weather. This is a paper that just came out September 15th, so what, 2 weeks ago? And this is the first fully coupled ocean atmosphere climate model that's pure AI. This just came out. And for those of you that are scientists and thinking like, oh, what's the point? These, I like to point out, the ocean model was led by an oceanographer at NYU, Lorzana led the team. And the atmosphere AI model was led by a leading atmospheric scientist in the field, Chris Brotherton. So these are scientists leading this charge, not purely AI experts. There are certainly AI people on the team, but I just like to point out the importance of understanding the physical system to lead to this. Okay, so one of the things we're doing with these AI models is we can make pretty pictures or pretty movies, but are they any good? So I've already mentioned that we know from our physical knowledge and simulations and Navier-Stokes on a rotating sphere that things like the Madden-Julian oscillation, this propagating storm, is important for giving us predictability in the mid-latitudes in the coming weeks. So one of the things we did with these AI models is we went in and said, what's going to happen if we just go put a heating blob like there's a storm in the tropics? Does it respond the right way as one of our physics-based models would? And if these AI models are learning garbage, it should blow up, it should explode, because it's never seen a world where we just put a big blob of heating that's a perfect ellipse, right? This has never happened in reality. We call these idealized simulations. So we put a heating blob in this model, and in fact, it gave us a beautiful wave pattern of high and low pressures, which is exactly what we expect from theory and from our physics-based models. This was surprising. I thought it was going to be an epic fail. So this is exciting. This means these models might be learning physics, at least some of it, under the hood. And you might say, why do I don't care about high and low pressure systems? Well, these are what lead to many of the weather extremes that we experience here. For example, the June 2021 North Pacific heat wave was driven by one of these high pressure systems sitting off the coast. And so my former master's student went in and said, how did these AI models do if they had existed back then? Could they have forecasted this event? So this is the observations of this heat wave in black, and the pink, see, it's pink again, and the purple show two different AI models. And while, yeah, they got hotter, do you see how they're a bit cold? So she actually looked at 60 heat waves across the US and found that the AI models were always too cold to what actually happened. And in fact, for those of you familiar, I'll nerd out for a second, this is a form of regression to the mean, in part because of how they're trained, but also my student Jacob just submitted a paper last week showing that these models are actually modeling the climate of approximately 20 years ago. And the reason is they've been trained over a data set, and about 1990, 2000 is right in the middle, right? So because of that, they're too cold because they don't have the most recent climate change we've been experiencing today. You can't see that in the video. All right. Another thing that we're doing is trying to, as I said, evaluate and predict these models. So unlike weather forecasting models, which have thrown many of those big companies through for a loop, is that predicting beyond weather is a different problem. And that's because the Earth system models have to remain credible under changing forcing, right? We know the climate is not static, it's not stationary. And when we get to these longer timescales, weeks, months, years in advance into the future, we can't ignore this warming world. So we have to assess if they're any good a different way. So here's an example. Actually, we've been looking at what's called the ACE AI climate model, which is an atmospheric model. We've been looking at tropical cyclones and trying to understand if they're getting the physics in there right for the right reasons. We're doing that with a variety of both. I might just brush through this quickly, but idealized studies again, where we go in and we put in idealized or fake heating blobs, synthetic heating blobs, and saying if it's getting the physics right, then it needs to show the right response to those heating anomalies. And in fact, on the left is the AI model's response to heating in a variety of locations, and the right is the physics-based model. And one, the amplitude's wrong, but two, the pattern's okay. What this means is, once again, it may be getting some of those climate relationships right for the right reasons. Okay. Now, I have a whole different talk that I could nerd out about later. Some of you might say, well, XAI sounds amazing. It's going to solve all of our problems. Actually, explainability, I think, is a bit of a misnomer. It implies that we are explaining the model. And actually, we're not. We're looking at blobby heat maps, right? We're looking at maps with reds and blues. And then as the human, we're trying to do the explaining. So there's still a big part for the human sitting there and coming up with what it's trying to tell us. And so one of the things my group is really focused on that I'm really interested in pursuing over the next few years is what we call interpretable models. And yes, this sounds like I'm slicing and dicing words, but it means something in the community. Interpretable means that they're mimicking the reasoning of like a human in a way that anybody could sit down and understand step by step how it got from A to B. Okay, and that's really hard to do. That is, mimic scientific human reasoning to improve intrinsic interpretability, thus reliability and trustworthiness. So one of the things we're doing, for those of you familiar, this is a form of soft attention, is we're actually saying, how would a climate scientist do forecasting? And what they do is they look at a map and they start to look for regions they know, like the tropical Atlantic, or, ooh, is ENSO in its El Nino phase or its La Nina phase? And if that's what the human would do, we're going to force the network to learn like that too, to learn by looking at specific regions of the globe for specific phenomena. I won't go into detail how we do that, but the point is, when we use this interpretable approach, we can once again take our full range of climate models and start to constrain them to make multi-year predictions, which is shown here in our yellow. So which way do we go now? So now I'm going to zoom way out and talk about some big areas I think that AI would be very exciting, and that some work that we're doing. So I don't have to tell you that there's a lot changing right now, right? And on top of this, the next decade will reveal AI, whether you like it or not, further embedding itself into society, right? Every aspect of society. It's certainly not just science. We're seeing that every day right now. All against this backdrop of a rapidly changing environment. And so in my group, one of the things and one of the reasons I'm excited to have just moved to Boston University is we're really working for more than just climate and weather science, I really want to work towards harnessing AI to anticipate human Earth system futures. So bringing the people part into it, doing that interdisciplinary work that is so hard to do. And so I'll talk a little bit about some of the work we're doing, and then I'll wrap up. So one of the things we're exploring is how exposure to compound climate hazards, you can think of it as hot and dry conditions, or heavy rains after a forest fire, right, which can cause mudslides. How are those transmitted globally by systems humans have set up, right? So by, say, trade networks, as an example, are one way that humans have now connected different parts of the world and thus also connected their climates. I'll show you a quick example. So we do some work where we're trying to see how calorie trade across different countries in the world are affected by these complex climate hazards. And in fact, by using our models, we can go in and talk about worst case scenarios of different countries, say 20, 30, 40, 70% of their calories in a given year being under climate threat. I think this kind of work is made much easier with AI being that glue I mentioned, of allowing us to talk with our economist colleagues, who again speak a different language than we do. Furthermore, motivated by the fact that global warming will continue over the decades ahead, research, you may have heard of this phrase of geoengineering, although I know it's the name of a department here in Minnesota, but in climate geoengineering, or climate intervention, is the concept of humans going in and intentionally changing the climate to try and counteract some of the worst impacts of climate change in hopes of getting our act together. So, for example, stratospheric aerosol injection, or putting aerosols into the stratosphere as a way of reflecting sunlight just a little bit in hopes of keeping temperatures from continuing to climb. This is an area of research where adopting interdisciplinary approaches is absolutely essential to gain a clearer understanding of the potential risks and benefits of such an approach. And to date, most of our climate model simulations studying this world assume that everybody has come together. Hold on, so this is stratospheric aerosol injection. But most of our scenarios to date assume the world has come together and agreed on one target we all think is best for the future of the Earth. And that's hard to swallow, right? And so instead, what we're doing is we're instead starting to say we need to simulate, to be clear, simulate worlds where we call them rogue actor worlds, where individuals or individual countries might actually consider doing this. And there are discussions on this now. But this is a computational challenge. We can't possibly simulate every possible way a rogue actor might do something in the future. And this is where AI comes in, allowing us, remember I said the 3 different reasons to use AI, this might be a reason to do something faster. So we can actually sample more of these scenarios in the same computational time. And then finally, we're doing some work trying to quantify the human footprint on the landscape. So to quantify the present and predict the future of human development and migration under climate hazards. So just as an example, this is a data set I'm really excited about. The second paper that I'll show you in just a second just got accepted this morning. So anybody want to talk about this data set, I'd love to. So there's something, especially in the biodiversity and ecology world, called the Human Footprint Index. So humans impact the landscape in many ways. We put up parking lots, right? We put up homes. We maybe put up a dam, okay? Many different ways. And you could talk about all those different ways, or they've come up with something called the Human Footprint Index, which is this one number between 0 and 1 that quantifies sort of how much humans are impacted that area. So 0 is, it's almost never been touched, or you can't see impact. And 1, I think of as like a mall parking lot, right? New York City, okay? So to come up with this number, it takes about 7 years to come up with a single estimation for 1 year of that number, because they collect data from the different countries, paperwork of where the farms are, et cetera, et cetera. That's a lot of work. It's been done for decades now. So there are a few of these data sets, of these snapshots available. So what we did is we said, this is amazing that all this work has been done, this painstaking work over many decades. Let's take it and use it to train AI, specifically to take in Landsat imagery, which we have right now, quite a lot of, and link it to this human footprint index. That is, take in Landsat imagery and predict this human footprint number. And the idea is, if we do that, we can get it for the year 2000 when we have a truth data set. But then we can use Landsat to then update and get a map for 2019 as well. And by looking, you probably can't see the difference, but it's really cool. Okay, I'll zoom in a second. They are different. I'll show you in just a second. But what's XAI have to do with this? XAI allows us to go in and say that this number actually doubled between 2000 and 2019, according to our algorithm. Why did it? We can once again make a heat map. The left is that Landsat imagery from the year 2000. The middle is the Landsat imagery from 2019. And the right is that heat map. Remember the cat? Heat map showing where the network looked to decide the human footprint went up. And when we look at that, we say, wow, it's looking largely at the road, right? To increase that human footprint, which is consistent with what we'd expect. Furthermore, it turns out this is the Trans-Sumatra Highway that it went in 2019, which is an exciting use case of something that these previous methods weren't able to capture because it happened too quickly. All right. Furthermore, we actually spent a long time, for those of you familiar with Landsat, figuring out which channels were important. And we use XAI to debug our network and figure out which ones to use. And we did this actually for many different locations. So I'll tell you, this is actually my husband on the left there, Pat Keys. He looked at 2,000 of these examples because I trained the AI and I said, I don't trust it. And he said, all right, well, the only way we can tell if we trust it or not is I'm going to look at it. So he did buy a special mouse and he zoomed around the data set night after night for many weeks, looking at all of these to make sure he as a human thought that this AI was working as well. And so there's these examples again of these heat maps showing us why the network increased its human footprint index. And I'm actually going to point out this bottom right-hand panel here in Indonesia. This one was particularly interesting because our truth data set told us that there was no human impact on this region, but our AI method said there was. It turned out the reason was what Pat had to do is he had to go in and use Google Translate to translate a local newspaper in the region and find out it was an illegal artisanal gold mine, okay, that was not written down in any records. And so our colleagues who made the original human footprint index had no knowledge of that. But because we were looking again from space with our algorithm, we were able to get the right answer. To be clear, I have a whole set of slides showing you places it fails miserably. I do not want to sell this as the end all be all. But that was an exciting use case. Okay, but now the new data set that just got accepted this morning, we have now done this for the past 24 years. So we now have a self-consistent data set of this human footprint index at a resolution of 30 meters. And it's publicly available for those interested. This is just a neat example of deforestation being replaced by croplands in the Amazon. But again, this is the idea of one number from 0 to 1 that can be very useful in lots of applications. I've actually started collaborating with folks who look at tiger movement, because tigers, it turns out, don't like to cross roads. And so this isn't, or anything sort of human impacted. And so this is a data set that they've started being interested in. Okay, so I'm going to wrap up. This has been a lot. So I will just say that I think the future of this big goal I have for sort of the rest of my career, and I hope many of yours, is to think about the future of this human Earth system science. And I really want to emphasize, in my view, the importance of interdisciplinary work to really bring humans into the picture of the Earth system science piece. We can't keep just modeling the physical system or just leaving social scientists to think about the human part. We really need to bring them together. And to do that, we're going to need people that can act as connectors, but I also think we need tools that can act as connectors. And I think that machine learning could be one of those tools. I think we need certainly more than that. And we need to be really talking with many of our colleagues to move forward in this space. So, and ultimately, to just bring it back to explainability and interpretability, at the end of the day with these networks and this machine learning approach, we want more than just a prediction. We want to know why. And so explainability and interpretability are going to be a really important part of the way forward. So thank you.
Thank you so much. Really, really interesting talk. So let's make sure we take some time here for a round of questions. I'm gonna ask Pete, you've been my runner in previous views for questions. That's also before anybody starts leaving. Thank the Kuehnast family for their support of the endowment and for being here. We wouldn't have engaging speakers like Dr. Barnes with us here. So again, really thank you, and we look forward to gathering with you tonight at dinner. So let's have questions for our speaker. If we can get the lights to come on, we'll do that. They seem to be delayed. Okay, so we're here. I'll make sure to shout out our students. Make sure students, if you feel like you can't ask a question, let's do away with that. Please, you want to get a question for everybody.
Hi, I have a master's in meteorology and going to school. I went to one of my best friends was a planetary scientist.
Yeah.
Have you tried this on in simpler planets like Mars or something?
Yeah, that's a great question. So I personally have not, but I would say like the astrophysics and the space community actually were one of the first in Earth science to jump on AI, just because they are a community that has so much data, they can't possibly have human eyes on all of the time. And so they've been at the forefront of some of this work. Right. So, and there are certainly, I would say the planetary atmospheric scientists, and now we're getting very specific. I think right there, one of the big issues is measurements. There's so few measurements that currently to date, I'm not sure many of these data hungry methods would be the most useful. Presumably, now I'm going to just make a conjecture. Once we can train some of these models to actually simulate the atmosphere with fidelity, like I mentioned, people are making progress on. The hope is that maybe we could then go and use some of these planetary atmospheres as use or test cases, right? If it's learning physics, then maybe we can go and actually test it on the few observations we have, as long as then we have issues with being too out of sample, of course, but so is climate change. So is the next 100 years likely to be out of sample. So that could be a really neat test environment. Yeah.
Thank you. I really enjoyed your talk. It seems that, you focus a lot on temperature.
Yeah.
And so my question is about how you deal with explainability and interpretability and other variables of climate that are more variable. So rather than like thinking about just the mean behavior, how do you take into account like the variability that is so much more extreme with regard to precipitation? And can you apply the same principles to precipitation that you did for temperature?
Yep. So first I will say in terms of temperature, I will just point out there's still high variance in temperature. We're actually in many of our use cases taking out the climate change signal. So we're only predicting the variance, not just the trend, which I could take a marker and draw that probably pretty easily. However, your point is, hold on, temperature seems like the simplest of all the variables to predict. I don't disagree. So what about precipitation? So we have many results with precipitation. It's way harder, surprising no one. It's noisier, not unsurprising, but also precipitation actually, not so much in my work, but in much of the work being done in sort of using AI and generative AI to make really high resolution imagery. That's where precipitation processes are really starting to be modeled, because it's so complex and nobody wants to know, and it will be average wet over the west coast of the US. They want to know, at sort of the county level or the city level, how much will it rain? So there are a lot of folks right now doing research specifically on high impact precipitation events with AI. I will say on the overall, what I've seen across timescales is these AI methods are on par with what we have to date. Nothing's been revolutionary, but I do think one of the exciting things has been what we call downscaling, or taking the data that we do have or the simulations we do have and putting it at that higher resolution that becomes more locally relevant. That's something that's computationally expensive and takes a really long time, and AI is showing us it can do it very quickly. So right now, I think the first big leap is just how cheap it is to get high resolution imagery of precipitation based on, say, our current forecast models. You know, I'm sort of around, but yes, people are working on preset.
I actually thought I had a question. Going back to you talked about your predictions of when we're gonna hit a certain threshold.
Yeah.
And one thing I guess I didn't quite catch in that is that prediction based on just is there temporal information going into that prediction that's getting you the gradient? Or is that prediction just coming from a snapshot and that's somehow extracting the?
Great question. It's the second. So we've given it the harder problem, which is you get a snapshot in time. How many years until we hit that threshold? Because if we gave it all the years before, it could just draw a line with a marker, if you will. With that said, you could argue that we're making it too hard because we do have past information, and why not use it? That was, and actually I'll turn this into a sort of a teaching point. You can tell my professor. We did that intentionally because ultimately what we knew already, we wanted to use XAI to look at the most important regions of the globe and learn where our climate models were relevantly biased. And in order to do that, if we gave it too much historic information, it would probably be able to get the answer too easily and sort of circumvent some of those biases. So we intentionally set it up that way. If our goal was the best prediction possible, maybe we would bring in time as well.
I have a loud voice.
Yeah.
You conclude with two sentences.
Yeah.
The future of human earth science.
Yeah.
System science requires interdisciplinary thinking.
Yeah.
And ultimately, we want more than just a prediction. We want to know why.
Yeah.
Well, this afternoon, we started with some comments by Jane Goodall, climatologist, anthropologist.
Yeah.
And it seems to me that certainly getting to know why is going to require work between you all and the earth sciences with social science. You had slides, copper mining, road building, deforestation. We need to be working with economists, psychologists, sociologists. We have two Kuehnast who are anthropologists, and I am an anthropologist.
Amazing.
So
This is great.
anyway, I would hope that those of you starting your careers would maybe be required to take some social science courses, because this is how we're going to start to answer a big answer to the why. Human behavior, human philosophy, human wants, human desires, human fear. Thank you.
Yes.
Hi, I was kind of wondering about if there's any more environmentally friendly ways of using AI, and how do you grapple with using a device that has such an environmental impact?
You mean in terms of energy use?
Yeah.
Yeah, great. This is a fantastic question. So a few comments on this. So one, first of all, every time any of us grab anything electronic, we're using electricity. Okay, let's be clear on that. Secondly, you're going to see a lot in the news right now about large language models, or LLMs, and honestly insane amounts of energy they are using. This is actually very different. And I'm not trying to say it's okay, but I just want to point out these are very, very different amounts of compute required. Actually, almost every result, except for the final one, was run on one of my grad students' laptops or my own laptop. All right, I didn't need a huge compute cluster in some big warehouse somewhere else. Okay, some cooling center. That's not to say some of the, those are of our work. I should be careful. NVIDIA's models are actually relatively compute heavy, but again, nothing like LLMs. So I will say this is a conversation that started a few years ago and actually wasn't about AI, but was about our climate models themselves. Our physics-based models take a lot of compute, especially if you've heard of the IPCC. The IPCC every 7 years or so is calling on many communities around the globe to run their own climate model. And when you add up all that compute, it's a lot. So this is something I think generally we need to just think deeply about as scientists. At what point is our weather model good enough? At what point, I mean, there was an article just a week ago that was at what point is the climate model we're running actually influencing the climate that we're trying to study, right? We're not there yet. Again, climate models are small compared to large language models. But I think should absolutely be a part of the discussion about AI. And I will say I have been disappointed when I bring that up on panels with some purely AI experts, because their responses often will do more good with it than without it. And my answer is that I think that's a cheap response. So great question. Keep asking that.
Yeah, it's a great question to provide to a lot of other areas too. As a polar scientist, the carbon that we
Oh, yeah.
use for our research, we use similar justifications. Well, if we weren't doing research, somebody would be doing something else.
We need to revisit that constantly. Yeah.
I may be asking a really challenging question here, so I'll apologize in advance for that, but I too sit firmly in the social science community. I'm a learning designer and I work for the University of Minnesota Extension.
Yeah.
So I spend my time driving all over Minnesota, spewing too much carbon, trying to work with communities to make decisions about climate change and incorporate climate science into their community planning, their farm planning, their decisions. I wonder if you can talk a little bit about how you envision AI will, or has the potential to become a fabric of that learning environment beyond just providing a better, faster data set or interpretation. How might we be able to fold that into the work we do with communities to help drive decisions or see things that aren't currently seeable?
I have a feeling you're better off answering this question than me. Because I think what you're asking me is beyond, the science. How might AI help us just in our daily interactions and communicating information? I am not even going to begin to touch on the importance of what you're asking, but I will point out already, I think one of the most powerful uses of AI I saw early on was a weather forecaster standing and showing a generated world with hurricane impacts of water rising and rising over a 6 or 12-hour period. And that people started watching in that video, that wasn't real, right? They just used AI to do it, watching the kitchen table get picked up, watching the lamp watching the human, like the water go above the human's head. So I do think for us as humans, and again, there are folks here that know more about this than I do, but at least for me, visually seeing that is very different than someone saying your house is going to have 6 feet of water in it. So I think visualization, going back to art, this was drawn by a human. I loved interacting with this particular artist. And so I would not say, we can just use AI art to communicate everything, but I do think there is something about also just creating visuals that maybe were not as straightforward for the physical scientists to make. That might be one way. Another big one is taking lots of complex knowledge out of many of these reports and then putting it into a language that people understand. I'm going to say that carefully because a lot of what they spew out is total garbage, right? And one of the first things when the large language models came out is my group ran into my office and said, look at all the papers that you've never published before, because they Googled my name. They're like, tell me about Professor Elizabeth Barnes. It's like, oh, she's amazing. And then it listed all these works, I've never done, but it all sounded plausible because it had picked up on certain words I had studied. So I say that very carefully. Maybe there's a future where it will help distill information. I know colleagues that are actually using it to mine climate reports to try and synthesize the information for different audiences, but I'm not there yet.
I'll just say, I
Yeah.
was really intrigued where you were starting to train models to look at the world in the way that people
Yes,
look at the world.
Yes.
And I think there's a real critical strength there, right?
I agree.
More-
yes. The challenge, I love, that's actually the area I'm moving towards. I love that. It turns out that's actually an area that the computer science world has also agreed is important. 10, 15 years ago, when deep learning really exploded, it was leave the model alone, let it learn what it needs to learn. And now we're realizing that then it overfits. It starts to get the right answers for the wrong reasons and then crashes later. And so now there's been a pullback to maybe we need to actually force it to learn certain ways so it stays within a credible realm. The downside to this is it's incredibly hard work and requires a human sit there and actually think through the problem. And that's a lot harder than just putting the data into the machine and turning the crank.
I see Kenny here, let's make sure we need 2 more questions. I'll say again, students, if any student wants to ask the last question, I would encourage that. So Kenny, one more, and then, yes, okay, we have our final question, and then we'll move to the atrium.
Thank you. Okay, 2 quick comments.
Okay, comments, okay.
Question.
Okay.
Want to put in a plug for geography, which is the ultimate interdisciplinary science. Where you can learn physical climate science alongside political
Yeah.
ecologists who are learning, about complex human systems. And also
That's great.
the American Meteorological Society does have an integrated, like atmospheric science, and social science program that, and it's, NCAR also used to have.
Yep.
My question is actually, so I had found our conversation earlier today fascinating, and your presentation fascinating, and I'm really intrigued, and also I have this question. So you ultimately train and produce a much better, more geographically precise, more hazard specific climate model.
Okay.
And will it affect policy at all? Do you comment on that presumed relationship between the accuracy of a projection and human action? Thank you.
Yes. No, I will not answer that question directly because I don't feel like I have the right background, but I'm gonna actually talk about the weather side. Actually, because we have a little experience with that and working with social scientists, talking to end users. And I think this is really important. Something I'm only just starting to grasp is a tiny effect, even if it's there, may not actually matter for the end user. So while the why and the science and the beauty of understanding the earth around us is part of our jobs, I do want to say that's an important part of what I do. If I then want to go and say, and it matters to society, I actually need to back that part up. And there are some of these changes, some of these predictions that I'm showing that when we go to the end user and say, what would you do if I could get you, 1% or 3% better? And their answer is, I would do nothing different than what you were giving me before. And I have typically not, again, talking with different types of people with different interests, etc. That's normally not been a bar. I just said, oh, it's 2% better. I win, right? Paper, here we go. And I think the bar of, is it useful? Is it new? Is it going to do something new? Requires we actually talk to the people using it, which are rarely the scientists in our field. So now, okay, so that's my answer there. You're talking about policy. Yeah, so I think, okay, I know how I'm gonna answer this. Okay, I'm gonna take it at an angle, but that's what you do in politics, right? One of the things I'm excited about here is a lot of the science we've done to date to hopefully inform policy has been in the mean, in the average. And in that scenario, I would argue, we know on average the globe is warming. And we know it's somewhere between by 2100, if that's a number you care about, somewhere between like 2 and 5 degrees. Okay, more on the 5 end, right? at the end of the day, if we want to keep talking about the average, then we're sort of done. Like we did it, it's hot, and we should do something about it, and that doesn't seem to be working. And now what people want is extremes at their local scale, and we can't give them that either because that requires we can predict the future daily weather out to 2100. So one of the things I'm really passionate about moving forward, and one of the things my group actually sort of demand that when I graduate students think of new research projects, that this comes into their thinking, is I don't want to predict the mean anymore. I want to think in terms of scenarios or stories or individual realizations. And I want to talk about what does the world look like to a person living then? And that could be it gets drier. And there's another scenario, I don't mean scenario like climate scenario, I mean storyline. There's another storyline where it gets wetter. Let's talk to our colleagues in economics, in social science, etc., to talk through what in health. What would that look like in your domain if the next 20 years did this, or if the next 20 years did that? And so I think that has the potential to influence some policies in a new way. I'm not going to say which ones, but because we don't do that sort of storylining very often in physical science, so it's more abstract when we talk about the mean. And so that is something that I'm very passionate about, and actually has come up quite a bit in our climate intervention work, because it's more like wargaming. Like we sit around and play a game of what if this happened, what would happen next? What would emergency planners do next? What would the hospitals need? And we can actually talk through that in a different way than if we said the average temperature was 2 degrees warmer. And so that's how I think some of the work we're doing right now can actually, really importantly, give us something to talk to at an interdisciplinary level with our colleagues about. Okay. Yeah.
Awesome.
Thanks.
Okay, we'll do one last question and then we'll give you a break.
Okay, great.
So I'm a grad student and I have like some very minimal modeling experience, but no experience with AI models.
Yeah.
And I think you were in one of the slides, you were comparing results from an AI model with a non-AI model. And you mentioned that you look for two things, amplitude and pattern. And the AI model was somehow better at pattern and not predicting patterns than amplitude.
Yep.
So is that typical in your world? And if an AI model is better at predicting patterns, would you consider that a better AI model? Like, is predicting patterns more valuable to you than amplitude?
Oof. Okay, I can answer the first part. So yes, it is common. So if the AI model isn't completely out to lunch, the first thing it's going to get is the pattern. Okay. But the amplitude, this is true actually with hurricanes, for example, they can get the pattern right, but the amplitude is way too weak. Okay. And actually there are nuanced reasons, but actually there's a really simple reason for the bulk of this, which is regression to the mean. If we train on root mean squared error, it does not want to stick its neck out and guess extremes. The best way to minimize RMSE, sort of stick to the average, okay? Stick to that very simple relationship you can, and that's indeed what we see. And so that is not what we found there is actually not unexpected, and it's actually pretty common. And a big push right now is how do we design loss functions so that's not as big of an issue. What was the second part of your question? I remembered it was harder.
So, like, is that typical in your world?
Yeah.
Also, like, if you find AI
Oh, which one's more important?
doing better
Yeah.
patterns, do you value that one? Like, which one is it?
Okay, I think my answer is going to be context specific. In the type of work I do, it doesn't mean anything to get the amplitude right and the pattern wrong. So I guess pattern has to come first, and then how big is the response? The question, maybe a different question, is if you get the pattern but it's too weak, is there still something you can do with that? And that again requires a lot of thought. So it does mean though it's learning something, which means maybe there's hope. Okay.
Okay, let's take this one. we can continue conversation outside for a little while. If you're joining us for dinner and you don't know how you're getting there, come find me, we'll figure that out. For me, yeah.